This is the EdExcel A-Level Maths Paper 2 from the 2024 series. Question number 1. Y equals 4x cubed subtract 7x squared plus 5x subtract 10. Part A, find in simplest form for the first part of part A dy over dx, and then for the second part of part A d squared y over dx squared. For part A, we begin with y equals 4x cubed subtract 7x squared plus 5x subtract 10. And so, for the first part of part A, if I differentiate to find dy over dx, differentiating 4x cubed, we end up with 12x squared. Differentiating negative 7x squared, we end up with negative 14x. Differentiating 5x, we end up with 5. Differentiating negative 10, we end up with 0. And so therefore dy over dx is equal to 12x squared subtract 14x plus 5. Now, for the second part of part A, to find d squared y over dx squared, we would have to differentiate with respect to x dy over dx. And so, differentiating 12x squared, we end up with 24x. Differentiating negative 14x, we end up with negative 14. And differentiating 5, we end up with 0. And so therefore, d squared y over dx squared equals 24x subtract 14. Part B. Hence find the exact value of x when d squared y over dx squared equals 0. Well, we know what d squared y over dx squared is. That's 24x subtract 14. And so for part B, we would have to set the 24x subtract 14 equal to 0. And solving for x, you will find x to equal 7 over 24. Question number 2. Jamie takes out an interest-free loan of £8,100. Jamie makes a payment every month to pay back the loan. Jamie repays £400 in month 1, £390 in month 2, £380 in month 3, and so on, so that the amounts repaid each month forms an arithmetic sequence. Part A. Show that Jamie repays £290 in month 12. For part A, if we know that in month 1 Jamie repays £400, the first term of the arithmetic sequence would be 400. So A, the first term of the arithmetic sequence, is 400. Now, in month 1, Jamie repays £400. In month 2, Jamie repays £390. In month 3, Jamie repays £380, and so on. You can see we decrease by £10 each consecutive month. So the common difference D is equal to negative 10. So to find out how much Jamie repays in the 12th month, U12, that will equal 400, the first term, plus 12 subtract 1, multiplied by negative 10. Meaning, the amount that Jamie repays in the 12th month is £290. After Jamie's nth payment, the loan is completely paid back. Part B. Show that n squared subtract 81n plus 1620 equals 0. In this question, we have to realize that we've paid back the loan completely. So we have to consider the sum of the arithmetic series. That is, Sn equals 1/2 n multiplied by 2a plus n minus 1 d, where a is the first term and d is the common difference. So using that formula for part B, we know that the loan is £8,100, which is Sn. So we have 8,100 equals 1/2 multiplied by n multiplied by 2a, so we have 2 multiplied by 400 plus n minus 1 multiplied by d, and we know what d is, that's negative 10. If we multiply through by 2, 8,100 multiplied by 2 is 16,200, and this is equal to n multiplied by the bracket here. Now if we simplify, we have 2 times by 400, which is 800, then we have n multiplied by negative 10, which is negative 10n, and then we have negative 1 multiplied by negative 10, which is positive 10. So we have 16,200 equals, now here we have n multiplied by 800 plus 10, so that's 810n, and then we have n multiplied by negative 10n, that's negative 10n squared. So we have 16,200 equals 810n, subtract 10n squared. And if I rearrange and simplify by dividing through by 10, we have n squared subtract 81n plus 1620 equals 0. Part C. Hence find the value of n. For part C, we would have to solve the quadratic n squared subtract 81n plus 1620 equals 0. If we go to the equation sub-menu, we have a polynomial of degree 2. We have 1 n squared subtract 81 n plus 1620 equals 0. So we have n being 45 or n being 36. So n is 36 or n is 45. Now, the loan will be paid at the first value of n, meaning n is equal to 36 only. Question number 3. The point P with x coordinate 3, y coordinate negative 2 lies on the curve with the equation y equals f of x, where x is a real number. Find the coordinates of the point to which P is mapped when the curve with equation y equals f of x is transformed to the curve with equation. For the first part of question 3, y equals f of x subtract 2. So, going from y equals f of x to y equals f of x subtract 2, we have a translation by vector to 0. Which means the new x coordinate of P, that will equal 3 plus 2, which is 5. The new y coordinate of P, that will remain as negative 2 because we are not doing anything in the y direction. Hence, the new coordinates of P will be 5, negative 2. For the second part of question 3, y equals f of 2x. So, for the second part of question 3, we are going from y equals f of x to y equals f of 2x. And here, the transformation is a stretch with scale factor 1/2 in the x direction. So, that means the new x coordinate of P will equal 3 multiplied by 1/2, which is 1.5. And because we are not doing anything in the y direction, the new y coordinate of P will equal negative 2, meaning the new coordinates of P will be 1.5, negative 2. For the third part of question 3, y equals 3 multiplied by f of negative x plus 5. First of all, let's go from y equals f of x to y equals f of negative x. Here, we have a reflection in the y-axis. Now, going from y equals f of negative x to y equals 3 times f of negative x, we have a stretch by scale factor 3 in the y direction. And now going from y equals 3 multiplied by f of negative x to y equals 3 multiplied by f of negative x plus 5, we have a translation by vector 0, 5. So, if we have a reflection in the y-axis, that means we need to multiply the x-coordinate of P by negative 1. So the new x-coordinate of P, that will equal 3 multiplied by negative 1, which is negative 3. Now, for the new y-coordinate of P, we need to begin by multiplying by 3. So we have negative 2 multiplied by 3, and then we add on the 5. So the new y-coordinate of P is negative 1, meaning the new coordinates of P will be 3, negative 1. Question number 4. A sequence u1, u2, u3, etc. is defined by un plus 1 equals kun subtract 5 and u1 equals 6, where k is a positive constant. Given that u3 equals negative 1, part A, show that 6k squared subtract 5k subtract 4 equals 0. For part A, we know that u1 equals 6. u2, that will equal k multiplied by u1 subtract 5. We know that u1 is equal to 6, so we have k multiplied by 6 subtract 5, which is 6k subtract 5. u3, that's equal to k multiplied by u2 subtract 5. So, knowing that u2 is 6k subtract 5, we have k multiplied by 6k subtract 5 subtract 5, and therefore u3 is equal to 6k squared subtract 5k subtract 5. We know that u3 is equal to negative 1, so we have 6k squared subtract 5k subtract 5 equals negative 1. And if I simplify this, you will find we have 6k squared subtract 5k subtract 4 equals 0. For the first part of part B, hence find the value of k. For the first part of part B, we are required to solve the equation 6k squared subtract 5k subtract 4 equals 0. Using our calculator to help us solve this quadratic equation, we have 6k squared subtract 5k subtract 4 equals 0, meaning k equals 4 over 3 or k equals -1/2. And we know that k is greater than 0, meaning the only value of k is 4 over 3. For the second part of part B, find the value of the sum of UR from r equals 1 to r equals 3. We know already what U1 is, that's 6. We know what U2 is, that's 6k subtract 5. And we know what U3 is, that's -1. So, knowing the value of k, we can now find what U2 is. So, U1 is equal to 6, U2 is equal to 6 multiplied by 4 over 3, subtract 5, which is equal to 3, and U3 is equal to -1. Therefore, the sum of UR from r equals 1 to r equals 3, that's equal to U1 plus U2 plus U3. So we have 6 plus 3 plus -1, which is 8. Question number 5. Given that theta is small and in radians, use the small angle approximations to find an approximate numerical value of theta multiplied by tan 2 theta over 1 subtract cos 3 theta. Where we have small angle approximations, sin theta is approximately equal to theta, cos theta is approximately equal to 1 subtract theta squared over 2, tan theta is approximately equal to theta, where theta is measured in radians. And so the approximate value of theta tan 2 theta over 1 subtract cos 3 theta, well, we have theta multiplied by, now tan 2 theta is approximately 2 theta. And then we divide this by 1 subtract cos 3 theta, well, cos 3 theta, that is approximately 1 subtract 3 theta squared over 2. So, for the numerator, theta times by 2 theta, that's 2 theta squared. For the denominator, 1 subtract 1, that is 0. Then we have negative 3 theta squared over 2, that is 9 theta squared over 2. And this will simplify to 4 over 9. Question number 6. Figure 1 shows a sketch of the curves with equations y equals f of x and y equals g of x, where f of x equals e to the 4x squared subtract 1, where x is greater than 0, and g of x equals 8 times the natural log of x, where x is greater than 0. For part A, find for the first part of part A f dash of x, and for the second part of part A g dash of x. So, for us to differentiate f, we would have to multiply e to the 4x squared subtract 1 by the derivative of 4x squared subtract 1. In other words, f dash of x will equal 8x, which is the derivative of 4x squared subtract 1, multiplied by e to the 4x squared subtract 1. So f dash of x is equal to 8x e to the 4x squared subtract 1. And now to differentiate 8 multiplied by the natural log of x, that will quite simply be 8 multiplied by 1 over x, which is 8 over x. So g dash of x is equal to 8 over x. Given that f dash of x equals g dash of x at x equals alpha, part B, show that alpha satisfies the equation 4x squared plus 2 times the natural log of x subtract 1 equals 0. To begin with, we have f dash of x equaling g dash of x. So we have 8x multiplied by e to the 4x squared subtract 1 equaling 8 over x. Now, if I divide through by 8x, we end up with e to the 4x squared subtract 1 equaling 1 over x squared. Now, if I take the natural log of both sides, we would have 4x squared subtract 1 equaling the natural log of 1 over x squared. And the natural log of 1 over x squared is the same as the natural log of x to the negative 2. If we now use the power law of logs on the right hand side, the natural log of x to the negative 2 is the same as negative 2 times the natural log of x. And so if we simplify, we can conclude 4x squared plus 2 times the natural log of x subtract 1 equals 0. And so alpha satisfies this equation. The iterative formula xn plus 1 equals the square root of 1 subtract 2 times the natural log of xn over 4 is used with x1 equaling 0.6 to find an approximate value for alpha. Part C, calculate, giving each answer to 4 decimal places, for the first part of Part C, the value of x2, and for the second part of Part C, the value of alpha. To begin with, we have the iterative formula shown here, and we know that x1 is equal to 0.6. So x2, that will equal the square root of 1 subtract 2 times the natural log of x1 over 4. We know that x1 is equal to 0.6, so we have the square root of 1 subtract 2 times the natural log of 0.6 over 4. And if we work this out, we have the square root of 1 subtract 2 times the natural log of 0.6 over 4, which is 0.7109239,143, and to 4 decimal places, that's 0.7109. Now, for the second part of Part C, the 0.7109 etc. is stored into the answer function. So now we have the square root of 1 subtract 2 lots of the natural log of the answer function over 4. And if I execute and then continue executing, you can see eventually we converge to 0.67 or 6 to 4 decimal places. So alpha is equal to 0.67 or 6. Question number 7. Figure 2 shows a sketch of the straight line L. Line L passes through the points A and B. Relative to a fixed origin, the point A has position vector 2i subtract 3j plus 5k. The point B has position vector 5i plus 6j plus 8k. Part A. Find the vector AB. The vector AB is equal to the vector OB, subtract the vector OA. So, the vector OB, that's equal to 5i plus 6j plus 8k, and we subtract from this the vector OA, which is 2i subtract 3j plus 5k. 5i subtract 2i, that's 3i. 6j subtract negative 3j, that's 9j. 8k subtract 5k, that's 3k. So the vector AB is equal to 3i plus 9j plus 3k. Given that a point P lies on L such that the magnitude of the vector AP is equal to 2 times the magnitude of the vector BP. For part B, find the possible position vectors of P. Now, if the magnitude of AP is twice the magnitude of BP, we could have P here, say, and then we know that AP is twice BP, so the ratios will be 2 to 1 for AP to BP. This means OP is equal to OA plus 2/3 of AB. So we have OA, which is 2i subtract 3j plus 5k, and we add on to this 2/3 of AB, which we have worked out to be 3i plus 9j plus 3k. So let's work this out. 2i plus 2/3 of 3i, that's 4i, negative 3j plus 2/3 of 9j, that's 3j, 5k plus 2/3 of 3k, that's 7k. So one possible vector for P will be 4i plus 3j plus 7k. Another way we could do this is, suppose P is over here. Now here we have AP being twice BP. So we have those ratios which are equal, that is, AB to BP is 1 to 1. So another vector for P will be OA plus twice AB. Now we know what OA is. That's 2i subtract 3j plus 5k. And we add on to this twice the vector AB, which we worked out to be 3i plus 9j plus 3k. So 2i plus 2 lots of 3i, that's 8i, negative 3j plus twice 9j, that's 15j, 5k plus twice 3k, that's 11k. So OP could also equal 8i plus 15j plus 11k. Question number 8. Part A. Prove that 1 over cosec theta subtract 1 plus 1 over cosec theta plus 1 is equivalent to 2 tan theta sec theta, where theta doesn't equal 90n degrees, where n is an integer. For part A, let's focus on the left hand side. On the left hand side, we have 1 over cosec theta subtract 1 plus 1 over cosec theta plus 1. And now, combining these fractions, we have 1 multiplied by cosec theta plus 1 plus 1 multiplied by cosec theta subtract 1 over cosec theta subtract 1 multiplied by cosec theta plus 1. Now, on the top, we've got cosec theta plus another cosec theta, and then we've got 1 subtract 1, so we end up with, on the numerator, 2 cosec theta, and for the denominator, cosec theta plus 1 multiplied by cosec theta subtract 1, that's quite simply cosec theta squared subtract 1. Now, we still have the 2 cosec theta for the numerator, but for the denominator, I can replace cosec theta squared with 1 plus cot theta squared, and then we still have the negative 1. So, for the denominator, 1 subtract 1 is 0, so we can simplify this to 2 cosec theta over cot theta squared. 2 cosec theta, that is the same as 2 over sine theta, and 1 over cot theta squared is the same as multiplying by tan theta squared. So we have 2 over sine theta multiplied by tan squared theta, and the tan squared theta I can replace with sine squared theta over cos squared theta. Now, sine squared theta over sine theta is just sine theta, and the cos squared theta is the same as cos theta multiplied by cos theta. So we can rewrite this as 2 over cos theta multiplied by sine theta over cos theta. And recognizing that 2 over cos theta is 2 sec theta, and sine theta over cos theta is tan theta, we end up with the result of 2 sec theta tan theta, which is indeed the right hand side, hence we've proved the result to be true. Part B. Hence solve for x being greater than 0 but less than 90 degrees the equation 1 over cosec 2x subtract 1 plus 1 over cosec 2x plus 1 equals cot 2x sec 2x. Give each answer in degrees to 1 decimal place. Now, you will find the left hand side of this equation is the same as the left hand side of the identity in part A. The only difference is, instead of us having a theta, we have a 2x instead. So we can use the result we have in part A to help us solve the equation in part B. So, for part B, we have this equation here. And what we can do is use the result from part A. And if I use the result from part A, replacing theta with 2x, we end up with 2 sec 2x tan 2x equals cot 2x sec 2x. We can divide both sides of this equation by sec 2x, leaving us with 2 tan 2x equals cot 2x. And the cot 2x I can rewrite as 1 over tan 2x. If I multiply both sides of the equation by tan 2x and then divide both sides of the equation by 2, we end up with tan squared 2x equals 1/2, and square rooting, we have tan 2x equals plus minus 1 over root 2. In the original domain, we had an x over here, but in our equation we have a 2x, so we need to adjust the existing domain. And so adjusting our new domain, we have 2x is greater than 0 but less than 180. Now here we have the graph of tan x and y equals 1 over root 2 and y equals negative 1 over root 2. We can use this graph to help us solve the equation tan 2x equals plus minus 1 over root 2. So let's find out what the values of 2x are. If I do the inverse tangent of 1 over root 2, we end up with 35.26, etc. So 2x will equal 35.26, etc. Now, If we change this, so we have the inverse tan of negative 1 over root 2, we come out with a value of negative 35.26, etc. And we'd have to reject this because it is not in the domain of 0 to 180. So to find the next value, we would have to add on 180 to this, leaving us with 144.73, etc. So 2x will also equal 144.73, etc. And so to find out what x is, we have to divide these values by 2 and give out what answer to one decimal place. So 35.26, etc. divided by 2, that gets us 17.6 degrees to one decimal place, and 144.73, etc. divided by 2, that will give us 72.4 degrees to one decimal place. Question number 9. The graph in figure 3 shows the path of a small ball. The ball travels in a vertical plane above horizontal ground. The ball is thrown from the point represented by A and caught at the point represented by B. The height, h meters, of the ball above the ground has been plotted against the horizontal distance, x meters, measured from the point where the ball was thrown. With respect to a fixed origin O, the point A has coordinates 0, 2, and the point B has coordinates 20, 0.8, as shown in figure 3. The ball reaches its maximum height when x equals 9. A quadratic function linking h with x is used to model the path of the ball. Part A. Find h in terms of x. We know a quadratic function linking h with x is used to model the path of the ball, meaning h will be of the form a multiplied by x subtract 9 squared, and the reason we subtract 9 is because the maximum point occurs when x equals 9, and then we add on b. If we use the point x equals 0, h equals 2, we have 2 equals a multiplied by 0 subtract 9 squared plus b. So we have 2 equals 81a plus b. If we use the point x equals 20, h equals 0.8, we have 0.8 equals a multiplied by 20 subtract 9 squared plus b. So we have 0.8 equals 121a plus b. We have two equations with two unknowns. We have 81a plus b equals 2 and 121a plus b equals 0.8. So we can solve these simultaneously to find a and b. We have a simultaneous equation with two unknowns. 81a plus b equals 2. 121a plus b equals 0.8. So we have the value of a, which is negative 0.03, and the value of b, which is 4.43. Knowing what a and b are, we can therefore conclude h is equal to 4.43 subtract 0.03 multiplied by x subtract 9 squared. Part B. Give one limitation of the model. For Part B, one limitation of the model is wind may affect the path of the ball. Chandra is standing directly under the path of the ball at a point 16 meters horizontally from O. Chandra can catch the ball if the ball is less than 2.5 meters above ground. Part C. Use the model to determine if Chandra can catch the ball. For Part C, we need to consider what the value of h is when x is 16. And substituting x equals 16 into the equation we found in Part A, we have h equals 4.43 subtract 0.03 multiplied by x subtract 9 squared. And if we work this out, 4.43 subtract 0.03 multiplied by 16 subtract 9 squared, that's equal to 2.96. And if we compare this with the 2.5, the 2.96 is greater than 2.5. Therefore, Chandra would not be able to catch the ball. Question number 10. Figure 4 shows a sketch of the curve C with parametric equations x equals t plus 3 squared, y equals 1 subtract t cubed, where t is greater than or equal to -2 but less than or equal to 1. The point P with coordinates 4, 2 lies on C. Part A. Use parametric differentiation to show that the tangent to C at P has equation 3x plus 4y equals 20. Well, if we use parametric differentiation, we have to differentiate y with respect to t and x with respect to t. And therefore, dy over dx will equal dy over dt over dx over dt. So, if we find out what dy over dt is, differentiating 1 subtract t cubed, we end up with negative 3t squared. And if we find out what dx over dt is, well, if we differentiate t plus 3 squared using the chain rule, we have 2 multiplied by t plus 3 to the power of 1 multiplied by the differential of t plus 3, so we multiply 2 lots of t plus 3 by 1, and therefore dx over dt equals 2 lots of t plus 3. So therefore, dy over dx that's equal to dy over dt, which is negative 3t squared, over dx over dt, which is 2 multiplied by t plus 3. Now, at the point 4, 2, if we substitute this into y equals 1 subtract t cubed, we can find the value of t. So we have 2 equals 1 subtract t cubed, and therefore we can conclude t equals -1. And knowing what t is, we can substitute this into dy over dx to find the gradient of the tangent. So dy over dx, that will equal -3 multiplied by 1 squared over 2 multiplied by 1 plus 3. And so we have dy over dx equaling -3 over 4. And if we use the point 4, 2, and using y minus y1 equals m multiplied by x minus x1, we have y minus 2 equals -3/4 multiplied by x minus 4. So if we multiply both sides by 4, we have 4y subtract 8 equals -3 multiplied by x subtract 4. And on the right hand side, if we expand the brackets, we end up with 4y subtract 8 equals -3x plus 12. And therefore, 3x plus 4y will equal 20. The curve C is used to model the profile of a slide at a water park. Units are in meters, with y being the height of the slide above water level. Part B. Find, according to the model, the greatest height of the slide above water level. So, if we consider figure 4, the greatest height is here, and this occurs when t equals -2. And with t equaling -2, we can use y equals 1 subtract t cubed to find the greatest height. So y max will equal 1 subtract -2 cubed, which is 9. So therefore, the greatest height is 9 meters. Question number 11. Figure 5 shows a sketch of part of the curve C with equation y equals 8x squared e to the -3x, where x is greater than or equal to 0. The finite region R, shown shaded in figure 5, is bounded by the curve C, the line with equation x equals 1, the x-axis. Find the exact area of R, giving your answer in the form a plus b e to the -3, where a and b are rational numbers to be found. To find the area of R, we have to integrate 8x squared e to the -3x in between 0 and 1. So let's think about the integral of 8x squared e to the -3x with respect to x. Now here we have two functions being multiplied by each other and we're integrating. So here we have to use integration by parts. U will equal 8x squared and v dash will equal e to the -3x. To find u dash, that's equal to 16x, and v, that's equal to the integral of e to the -3x, which is -1/3 e to the -3x. So when we integrate 8x squared e to the -3x with respect to x, well, we have u, which is 8x squared, multiplied by v, which is -1/3 e to the -3x, subtract the integral of u dash, which is 16x, multiplied by v, which is -1/3 e to the -3x with respect to x, and we add on a constant of integration plus c. So 8x squared multiplied by -1/3 e to the -3x, that's -8/3x squared e to the -3x. And then we add on, and the reason we add on is because we've got a negative, then we have 16 times by a third, so we add on 16/3, and then we've got the integral of x e to the -3x with respect to x, and then we add on a constant of integration c. And so to integrate x e to the -3x with respect to x, here again we'd have to use integration by parts. So the integral of x e to the -3x with respect to x, well, u will equal x, v dash will equal e to the -3x, u dash is equal to 1, v is equal to -1/3 e to the -3x. So now we have enough information to work out the integral of x e to the -3x with respect to x. So we have the integral of x e to the -3x with respect to x, that's equal to u, which is x, multiplied by v, which is -1/3 e to the -3x, subtract the integral of v, which is -1/3 e to the -3x, multiplied by u dash, which is 1, with respect to x, plus some constant of integration k. So we have x multiplied by -1/3 e to the -3x, that's -1/3 x e to the -3x, and then we've got negative and a negative, which makes a positive, so we add on the integral of 1/3 e to the negative 3x with respect to x. So we have negative 1/3 x e to the negative 3x, and then integrating a third e to the negative 3x with respect to x, we end up with negative 1/9 e to the negative 3x plus a constant of integration k. Now that we know what this result is in blue, we can therefore work out the integral of 8x squared e to the negative 3x with respect to x. So the integral of 8x squared e to the negative 3x with respect to x, well, we have the negative 8/3x squared e to the negative 3x plus 16/3 multiplied by the result here of negative 1/3 x e to the negative 3x, subtract a 9th e to the negative 3x plus a constant of integration c. So we've got negative 8/3x squared e to the negative 3x, and then I need to multiply the blue bracket by 16/3. So we have negative 16/9 x e to the negative 3x, subtract 16/27 e to the negative 3x plus c. And if I factorise out a negative e to the negative 3x, inside the bracket we've got 8/3x squared plus 16/9x plus 16/27 plus the constant of integration c. Therefore, the area of R will equal the integral of 8x squared e to the negative 3x with respect to x between 0 and 1. So, evaluating this integral, we have negative e to the negative 3x multiplied by 8/3x squared plus 16/9x plus 16/27, and then we need to evaluate this between 0 and 1. So substituting in 1 for our lower limit, we have negative e to the negative 3 multiplied by 1 multiplied by 8/3 multiplied by 1 squared plus 16/9 multiplied by 1 plus 16/27. For our lower limit, we have negative e to the 0 multiplied by 16/27, because when I substitute in 0 into 8/3x squared and 16/9x, I end up with 0. And then we need to find the difference between these. So let's work out this bracket. I have 8/3 multiplied by 1 plus 16/9 multiplied by 1 plus 16/27. That's 136/27. And then I'm multiplying that by minus 1. So I've got minus 136/27 e to the negative 3. And then here I've got a negative and a negative which give a positive. E to the 0 is 1. So I add on 16/27. Therefore, the area of R is equal to negative 136/27 e to the negative 3 plus 16/27. Question 12, Part A. Express 1/v multiplied by 25 subtract v in partial fractions. So for Part A, we can write the 1/v multiplied by 25 subtract v as a/v plus b/25 subtract v. And if I multiply both sides by v multiplied by 25 subtract v, on the left hand side we have 1, on the right hand side we have a multiplied by 25 subtract v plus b multiplied by v. Now, when v equals 0, we have 1 equals 25a, meaning a is 1/25. And when v is 25, we have 1 equals 25b, meaning b is 1/25. Knowing what a is and knowing what b is, we can rewrite 1/v multiplied by 25 minus v. So we can conclude 1/v multiplied by 25 subtract v is equal to 1/25v plus 1/25 multiplied by 25 minus v. The volume v microliters of a plant cell T hours after the plant is watered is modelled by the differential equation dv/dt equals 1/10 v multiplied by 25 subtract v. The plant cell has an initial volume of 25 microliters, part B. Find, according to the model, the time taken in minutes for the volume of the plant cell to reach 24 microliters. For part B, we have dV over dt equals 1 over 10V multiplied by 25 minus V. And if we separate the variables and then integrate, we have the integral of 1 over V multiplied by 25 subtract V with respect to V equals the integral of 1 over 10 dt. And we can use the result from part A to rewrite the left-hand side of this equation. So using part A, we have the integral of 1 over 25V plus 1 over 25 multiplied by 25 minus V with respect to V equals the integral of 1 over 10 with respect to t. And if I factorise out a 1 over 25, I've got 1 over 25 multiplied by the integral of 1 over V plus 1 over 25 minus V with respect to V equals 1 over 10 integrated with respect to t. So we've got 1 over 25. Now integrating 1 over V, we end up with the natural log of V, and integrating 1 over 25 minus V, we end up with minus the natural log of 25 minus V. And on the right hand side, integrating 1 over 10 with respect to t, we end up with 1/10 t. And then we add on a constant of integration plus c. Now on the left hand side, we've got natural log of V subtract the natural log of 25 minus V. So we can use the subtraction law of logs to simplify this. So we've got 1 over 25 multiplied by the natural log of V over 25 minus V equals 1/10 t plus c. We know from the question the initial volume of the plant cell is 20 microliters. So when t equals 0, V equals 20, meaning we have 1 over 25 times the natural log of 20 over 25 minus 20 equals 1/10 times 0 plus c. And from this we can conclude that c is equal to 1 over 25 times the natural log of 4. And knowing that, we can replace this c with 1 over 25 times the natural log of 4. So we've got 1 over 25 times the natural log of V over 25 minus V equals 1/10 t plus 1 over 25 times the natural log of 4. What we need to do in the question is find the time taken to reach 24 microliters. So when V equals 24, we need to find out what t is. And if I substitute in 24 into this equation, we've got 1 over 25 times the natural log of 24 over 25 minus 24 equals 1/10 t plus 1 over 25 times the natural log of 4. So let's find what t is. Here we have 1 over 25 times the natural log of 24 over 25 minus 24, and then I subtract 1 over 25 times the natural log of 4, and then I multiply this by 10, so you will find t to equal 0.716 etc. hours. So in minutes, if I multiply through by 60, we've got 43 minutes. Part C, show that V equals A over e to the negative kt plus b, where a, b and k are constants to be found. If we consider this equation 1 over 25 times the natural log of V over 25 minus V equals 1/10 t plus 1 over 25 times the natural log of 4, we need to rearrange for V in this equation. And for that, let's take this 1 over 25 times the natural log of 4 to the left hand side. So we have 1 over 25 times the natural log of V over 25 minus V, subtract the natural log of 4 over 25 equals 1/10 t. Now we can use the subtraction law of logs again. Noticing we have a 1 over 25 in both this term and this term, we've got 1 over 25 times the natural log of. Now here we've got v over 4 lots of 25 minus v. And on the right hand side, we've got a 10th t. So we've got 1 over 25 times the natural log of. Now here we've got v over, well, 4 over times 25, that's 100. 4 times minus v, that's minus 4v. And on the right hand side, we've got a 10th t. Now, if I multiply both sides by 25, I've got the natural log of v over 100 minus 4v equals 2.5t. If we now anti-log both sides, we've got v over 100 minus 4v equals e to the 2.5t. So, if I multiply both sides by 100 minus 4v, we end up with v equals e to the 2.5t multiplied by 100 minus 4v. And if I now expand the brackets on the right hand side, we have 100 e to the 2.5t, subtract 4v e to the 2.5t. If I get everything with a v on one side, everything that doesn't contain a v on the other side, we've got v plus 4v e to the 2.5t equals 100 e to the 2.5t. And on the left hand side, I can factorize out a v, leaving me with 1 plus 4 e to the 2.5t inside the bracket, and this is equal to 100 e to the 2.5t. Now let's divide both sides by 1 plus 4 e to the 2.5t. So we have v equals 100 e to the 2.5t over 1 plus 4 e to the 2.5t. And now what we need to do is divide each term by e to the 2.5t. So I have v equals 100 e to the 2.5t over e to the 2.5t, which is 100. 1 divided by e to the 2.5t, that's e to the negative 2.5t, and 4 e to the 2.5t over e to the 2.5t is just 4. And therefore, v equals 100 over e to the negative 2.5t plus 4. The model predicts that there is an upper limit, L microliters, on the volume of the plant cell. Part A, find the value of L, giving a reason for your answer. Here we need to consider what happens when t tends towards 0. Well, when t tends towards 0, v will tend towards 100 over, now here, as t tends towards 0, e to the negative 2.5t tends towards 0, and then I've got plus 4. 100 over 4 is 25, so this is equal to 25. So therefore, L is 25 microliters. Question number 13. The world human population, p billions, is modelled by the equation p equals ab to the t, where a and b are constants and t is the number of years after 2004. Using the estimated population figures for the years from 2004 to 2007, a graph is plotted of log base 10 of p against t. The points lie approximately on a straight line, with the gradient 0.0045, the intercept 0.81 on the log base 10 p-axis. Part A. Estimate to 3 decimal places the value of A and the value of B. Here, the straight line will be of the form y equals mx plus c. But instead of a y, we've got log base 10 of p, and instead of an x, we've got a t. We know the gradient and we know the, effectively, y-intercept. So we've got log base 10 of p, which is essentially our y, equals 0.81, which is the, effectively, y-intercept, plus 0.0054, which is the gradient, multiplied by t. So this equation is of the form y equals mx plus c. So if we antilog both sides, we've got p equals 10 to the power of 0.81 plus 0.0054t. So what this is the same as is 10 to the 0.81 multiplied by 10 to the 0.0054t. So let's work out what these are to 3 decimal places. We've got p equals 10 to the power of 0.81 0.81, that is 6.457 to 3 decimal places. And then we've got 10 to the power of 0.0054, which is 1.013 to 3 decimal places, and we raise this to the power of t. Hence, the value of A is 6.457 and the value of B is 1.013. In the context of the model, for the first part of part B, interpret the value of the constant A, and then for the second part of part B, interpret the value of the constant B. So, A is the population in billions in 2004, and B is the rate at which the population increases per year. Part C. Use the model to estimate the world human population in 2030. So for part C, going from 2004 to 2030, that's 26 years, so t is 26. So we have p equals 6.457 multiplied by 1.013 to the power of 26. Working this out, we have 6.457 multiplied by 1.013 to the power of 26, we get 9.03, etc. So the population is approximately 9 billion to the nearest integer. Part D. Comment on the reliability of the answer to Part C. For Part D, the answer is not very reliable as 2030 is a long time since 2004 to 2007, which the model is based on. Question number 14. The circle C1 has equation x squared plus y squared subtract 6x plus 14y plus 33 equals 0. For part A, we have to find the coordinates of the centre of C1 and the radius of C1. For part A, we begin with x squared plus y squared subtract 6x plus 4y plus 33 equals 0. And to find the centre and the radius, let's begin by completing the square in the x and in the y. So, completing the square in the x, we've got x subtract 3 squared, subtract the square of 3, and in the y direction, we've got y plus 7 squared, subtract the square of 7, and then we add on this 33, and this is equal to 0. So I've got x subtract 3 squared plus y plus 7 squared equals, now here I've got negative 33 plus 49 plus 9, which is 25. The 25 I can rewrite as 5 squared. So I've got x subtract 3 all squared plus y plus 7 squared equals 5 squared. So the centre is given by 3 negative 7 and the radius is equal to 5. A different circle C2 has centre with coordinates negative 6, negative 8, has radius k where k is a constant. Given that C1 and C2 intersect at 2 distinct points, part B find the range of values of k, giving an answer in set notation. For part B, here is a diagram explaining what we have. We've got the circle C1 shown in black, and here we've got the circles C2 and the different possibilities of C2. C1 has centre 3, negative 7, and C2 has centre negative 6, negative 8. Here we've got the radius of C2, k max, and anything smaller than k max will mean C1 and C2 intersect. Or for the little circle, we've got the radius of k, and anything bigger than this minimum value means C1 and C2 would intersect. The first thing we need to do is find out the distance between the centres. The distance between the centres, we've got the square root of negative 6 subtract 3 squared plus negative 8 subtract negative 7 squared. So we have the square root of negative 6 subtract 3 squared plus negative 8 subtract negative 7 squared, which is root 82. Now we know C1 has a radius of 5, so to find out what kmin is, what we need to do is, well, we've got this distance of root 82, and if I take away the 5, I get kmin. So kmin is equal to root 82 subtract 5. And to find out what kmax is, well, I've got the distance between the centres being root 82, and then I need to add on this extra bit over here, which I know is 5. So kmax is equal to root 82 plus 5. So the range of values for k, we've got k being greater than root 82 subtract 5, but less than root 82 plus 5. Question number 15. The curve C has equation x plus y all cubed equals 3x squared subtract 3y subtract 2. Part A, find an expression for dy over dx in terms of x and y. So for part A, we've got x plus y all cubed equals 3x squared subtract 3y subtract 2. Now I need to differentiate this implicitly. So I've got the x plus y all cubed. If I differentiate that with respect to x, well, I've got 3 multiplied by x plus y squared multiplied by the differential of the bracket, which is 1 plus dy over dx. On the right hand side, differentiating 3x squared with respect to x, I end up with 6x. Differentiating negative 3y implicitly with respect to x, I end up with negative 3 times dy over dx, and differentiating negative 2, I end up with 0. Now, let's gather everything with the dy over dx on one side and everything that doesn't contain a dy over dx on the other side. So, I've got 3 multiplied by x plus y all squared times dy over dx, so that's this term multiplied by dy over dx, and I'm going to add to this 3 multiplied by dy over dx. And on the right hand side I'll have the 6x, and then I'm going to subtract from this 3 times x plus y all squared times by 1. So I'll subtract 3 multiplied by x plus y squared. Now, if I factorise out a dy over dx, inside the bracket I'd have 3 times x plus y all squared plus 3. And on the right hand side I'd have 6x subtract 3 times x plus y squared. And if I divide through by 3 lots of x plus y all squared plus 3, we'd have dy over dx equaling 6x subtract 3 times x plus y all squared over 3 times x plus y squared plus 3. The point P with coordinates 1, 0 lies on C. Show that the normal to C at P has equation y equals negative 2x plus 2. So, at the point P with coordinates 1, 0, dy over dx equals 6 times by 1, subtract 3 times by 1 plus 0 squared over 3 times by 1 plus 0 squared plus 3. And if I work this out, I get 1/2. This 1/2 is the gradient of the tangent, so the gradient of the normal is negative 2. So, using y minus y1 equals m times by x minus x1, I've got y subtract 0 equals negative 2 multiplied by x minus 1. And if I expand and simplify, I end up with y equals negative 2x plus 2. Part C. Prove that the normal to C at P does not meet C again. You should use algebra for your proof and make your reasoning clear. Here we have the equation of the normal to C at P, and here we've got the curve C. We need to substitute this into this. In other words, substitute in equation 2 into equation 1. So, I've got x plus negative 2x plus 2 cubed equals 3x squared subtract 3 times by negative 2x plus 2 subtract 2. So I've got this, which simplifies to 2 subtract x, then I cube it, and this is equal to 3x cubed, and then if I expand the brackets here I get plus 6x subtract 6, and then I subtract 2. So I've got 2 subtract x cubed equals, here I've got 3x squared plus 6x, and then here negative 6 subtract 2 is negative 8. Now the 2 subtract x cubed I can rewrite as 2 subtract x squared times by 2 subtract x. And on the right hand side that remains the same as 3x squared plus 6x subtract 8. Now I'm going to expand the 2 subtract x squared. I end up with x squared subtract 4x plus 4, and I still multiply this by 2 subtract x, and this is equal to 3x squared plus 6x subtract 8. Now, what we need to do is expand the brackets. So here I've got x squared times by 2, which is 2x squared, x squared times by negative x, that's negative x cubed, negative 4x times by 2, that's negative 8x, negative 4x times by negative x, that's positive 4x squared, 4 times by 2 is 8, and 4 times negative x is negative 4x, and this is equal to 3x squared subtract 6x subtract 8. So what we need to now do is simplify everything and gather everything over to one side and set the other side equal to 0. So I've got x cubed subtract 3x squared plus 8x subtract 16 equals 0. So if I call this equation 3, I know that P with coordinates 1, 0 intersects 3, meaning I've got an x coordinate of 1 and a y coordinate of 0, and notice this 0 corresponds to this 0, meaning x subtract 1 is a factor of f of x equals x cubed subtract 3x squared plus 8x subtract 16. Now, what I can do is recognize then that x minus 1 multiplied by some quadratic will be equivalent to x cubed subtract 3x squared plus 8x subtract 16. Now, we can use inspection to help us find out what this quadratic factor is. I've got negative 1 multiplied by something equals negative 16, so that is positive 16. And here I've got negative 1 times x squared, which is negative 1x squared. Here I've got a negative 3x squared, so I need to subtract another 2x squared. So here then, I would have negative 2x. So I've got x subtract 1 multiplied by x squared subtract 2x plus 16 being equivalent to x cubed subtract 3x squared plus 8x subtract 16. Now, if I set this equal to 0, because this equation is equal to 0, then I've got x subtract 1 multiplied by x squared subtract 2x plus 16 equals 0. I know that one of my solutions is x equals 1. Now, if I consider the x squared subtract 2x plus 16 equals 0, let's see how many roots this has. If I use the discriminant, I've got negative 2 squared subtract 4 times by 1 times 16, and this is equal to negative 60. And because the discriminant is less than 0, I can conclude that x squared subtract 2x plus 16 equals 0 has no real roots. Meaning x equals 1 is the only solution to 3, and therefore the normal to the curve at P never meets the curve again.